So it's been a long time since I've made a video on differential topology, but I have an excuse, as much as everybody loves those. I found some really cool papers that addressed some very important generalizations of smooth manifolds, which were the object that I was going to center my exposition of the subject around last time I began talking about the subject. Since then, like I said, I've discovered these spaces, and I think that pedagogically it makes more sense to learn about them instead, because those are really the most general spaces which we can define smoothness on. There, it's the essence of smoothness is where we find it, is in those new spaces. So I'm going to start out today by discussing the definitions of the spaces involved, just sort of like how I began last time by talking about the definition of a smooth manifold. Except this time, instead of having just one type of space that we're going to be concerned with, there's actually 3 different types of spaces, which might sound a little bit more complicated right off the bat, but it turns out there's a whole lot less machinery going into each and every single one of them. So this episode should actually be quite a bit shorter than the original one, and it should be easier to follow. The way I define my smooth structure will be simpler. I won't have to end up using all of those equivalence relations to define maximal structures and so on and so forth. All of that is entirely unnecessary because we're going to be a whole lot closer to the set theoretic essence of what's going on here. Just sort of like how when you start general point set topology and you break it down to nice set theoretic axioms, and it starts to look a whole lot more like taking set theory class. Okay, so now that that has been explained, let me get on with the show, which is to explain the list of definitions that we're going to need before I can get to the actual definitions that we're going to need for today. The definitions of Sikorsky, Sorrow, and Frolicker spaces. And I am sorry if I'm mispronouncing any of those names. I've only ever read them, never heard them pronounced in speech. So it's very entirely possible, especially Sorrow. I'm totally sure I'm saying that wrong. It could be Sauro. Yeah, anyway. So here are the preliminary definitions that I'll need before I can get to the definitions of those spaces. And the first one here, you probably already recognize, but I felt like putting it in just to be self-contained. The definition 1 is that a function, f here, is going to be called constant if for any choices of elements in its domain, the output is equal, which is what I have expressed here with this equation and this for any element, 2 elements in X. All right. So that, that's not too hard. Everybody's encountered constant functions before. Generally, when studying calculus, it's your favorite type of function, because when you find a constant function, you know that derivatives don't care about him. You could pull him out of derivatives. You could take the derivative and just send it straight to 0. It's lovely. Constants make your life so much better when you're in calculus, and constants are definitely going to be a part of differential topology. We really care about having access to them because constants should be smooth. And so we need to sort of get a handle on that in order to define an abstract notion of smoothness. All right, so on to definition 2 now. This one is a whole lot less familiar looking. This is the definition of the property of locality, which is going to be figuring heavily in 2 of the 3 definitions that we need for our spaces. So let's start unpacking this absolute monster of a definition then. Okay. So a family of maps, F, which is equal to, here I've got it written as an indexed set of maps Fi, going from domains Xi to Yi. And this is just so that you all can recognize that not every domain or codomain in this set has to be the same. The property of locality doesn't require all maps going into the same set or all maps coming out of the same set. Okay. So this map, this big set F of maps, has the property of locality if it is true, if the following statement's true, that whenever I've got a map F star, and hopefully you can see this, it's written a little small, but F star belongs to the union of the set of all maps going from some domain that's contained in big F to some codomain that's in big F. So F star is just a map. It's just a map between sets. And the sets that it's moving between happen to also be codomains and domains in big F. Not necessarily of the same function in big F. They don't have to do that. They just have to be codomains and domains belonging to that first family. Okay, so I've got this F star, and if it's true that, and I've also made a choice of topology on every single one of my domains. I sort of suppressed that because that was that happened before this next step, but that's going to be important for what I'm about to do next. I need to find some open cover, this index family right here of ULs, of the domain of my function F star, which remember is one of the domains from here. So if I can find an open cover of him, like this one, and a set of and a set of functions right here, phi L, parameterized by the same L, such that these functions, and I haven't written it here, but I should have, these functions actually all belong to big F. So I found this open cover and this list of functions, both indexed by the same index, and it's true that F star, when restricted to members of this open cover, is exactly equal to one of my functions here restricted to a member of my open cover. If I can find an F that has all of these properties, I can find that open cover, I can find this family of functions, and it's equal on all of these pieces, then F star should be in big F if big F has the property of locality. That's what it means to be local. If you look like one of the maps in this family of maps, if I can zoom in on any one spot and it looks like you are exactly one of the maps in here, then you are one of the maps in here. That's what it means to be, for a set of maps to be local. And once again, it doesn't depend on all of them going into or out of the same family of sets. That's going to be very important for the definitions that I have coming on here. All right, so now that I've gotten these preliminary things out of the way, let's talk about the actual spaces that we're interested in. So now that we know what locality means, and now we know what constants mean, though I bet we all probably knew that, we can actually start talking about these spaces. So before I go on, for every single one of these definitions, it's going to be the case that X is going to be talking about or is going to be the label for a non-empty set, and I'll generally be calling that thing the space. P here, he's going to be some, and I don't, yes, he's going to be a subset. I do have this written correctly. He's a subset of this family of maps, which is the union of all of the sets of maps from any Euclidean space into my non-empty set X. So in my family of maps P, there could be any number of functions that map from the line, the plane, three-dimensional space, 50-dimensional real space into my set X. And I will call this family of maps P, that maps from all the different Euclidean spaces into X, I will call him the family of plots of X. Likewise, I'll have C, and I didn't write it down here because I'm an absolute scatterbrain, but C is sort of like the opposite. Here, it's the same sort of thing, a union over the natural numbers of all these different sets of maps, but here it's the sets of maps that are taking points from X into some Euclidean space of some dimension. So in C, I'll have a whole bunch of maps that take things from my space into the plane, or into R3, or into R472. And these guys, whereas P was called the family of plots, these folks will be called the family of coplots because they're dual to the plots. Where the plots went into my space, the coplots go out of my space. Okay, so now that we've got all of those notions talked about, those are going to be conventions in each one of these definitions. Now let's get on to the definitions. So this is the third definition I've presented so far, and it's going to be that of a Serow space, which is the first of these couple of spaces that I managed to find for myself. This definition is entirely unmodified. The next definitions that I found, I have modified them slightly to sort of be more symmetric with this guy. But I will show you in the next episode that they're actually equivalent to their original definitions, because that would be a good mathematician thing of me to do. It doesn't really make sense to just call them one thing that already has a definition name when I'm using a different definition if it isn't the same thing. So I will be verifying that for you. Anyway, without any more further prelude to this, Daisy, she's scratching at my door. Give me a second. I can't let her ruin this take. Excuse me. I'll just do this until she realizes she doesn't want to scratch at things. Okay, so one of these Serow spaces is going to be a pair, xp, where, like I said, P is a family of plots, and X is just a non-empty set. And then P is going to have to satisfy some rules in order for this pair to actually be a Serow space. So P contains every single constant map that could possibly exist from a Euclidean space into my set X. So that's the first thing. That's generally referred to as the covering axiom, because it means that the entire space is actually covered by maps, regardless of any other property that you give to the family of plots. Just be quiet, okay? Yeah. All right. So now that's the first property. We've got all the constant maps. The second property is that given any member of my plots, remember it's just a map that's taking values from some Euclidean set, some Euclidean space of some dimension, into my set X. So in order to capture the idea that these things are smooth, this family P has got to be closed under the next type of operation. Namely, if I've got this plot P belonging to my family of plots, and I know that the dimension of its domain is some number n, then given any choice of 9 smooth functions going from R to R, if I Cartesian product those functions all together and then compose them on the domain side of my original plot, this guy has got to be in my family of plots. Which is to say that, like, composing smoothly on one side doesn't unmake a smooth function. And this is just a property of smooth maps that we need these things to have if they're going to generalize smoothness. Whenever you take two smooth maps and compose them together, the new map that you get is also smooth. And if I was able to take one of these plots and compose it on one side with a smooth map and get something that wasn't smooth, then no dice. So that's why this property is showing up. And then finally, there was a reason why I defined that whole gigantic locality definition as my second definition, and it is because of number 3 here. P possesses the property of locality, and for what choice of topology on its domains? For the standard topology on every single one of those Euclidean domains in it. So no, don't need to find some sort of weird, obscure choice of topology, but it is that big, long, crazy property that I gave you before, and every single family of plots in one of these Serow space pairs has to have the locality property. All right, and so one of these pairs with these three properties makes a Serow space. I have yet to show it. It'll be a feature of one of the next episodes, but these guys are categories, and in fact, this is all I need. I don't need any other properties in order to find smooth maps between these spaces. So there's our first definition of a smooth space. Let's get on to the next one. I'm trying to record. This dog is trying to bark. We need to come to some sort of compromise. I imagine, yes, a big yawn. I imagine it involves lots of scratching, unfortunately for me. So, now that we've gotten Serow space out of the way, let's start talking about Sikorsky spaces. So, definition 4 here. A Sikorsky space is going to be a lot like a Serow space, where it's talking about a pair, a set, and a family of maps. Except that now it's going to be the pair of with X and a family of coplots, C. But the three rules are going to look very similar that this pair has to actually obey. Once again, C contains all of the constants in that big union that it happens to be a subset of. Moreover, just like before where I could take any list, or I could take any plot and then smoothly compose it with a list of functions to get another plot, I can smoothly compose any coplot with some list of smooth maps on its codomain side to get another coplot. Coplots are also they're also closed under this idea of smoothly composing maps, but instead of smoothly composing them on the domain side, we smoothly compose them on the codomain side. Blech, I'm falling all over my words. All right, so that's rule 2. And then finally we have rule 3 again. This guy's showing up all over the place. C obeys the property, or rather possesses the property of locality, but here the topology that he happens to obey, or rather possess locality in, is the initial topology on the set X that he actually generates. So that's the topology with the fewest number of open sets, such that every single map in the family of maps C is actually continuous. So that will be the 3 conditions that force a pair of a set X and its coplots on it to be a Sikorsky space. And like I said before, this isn't exactly the definition that Roman Sikorsky wrote down oh so long ago when he first started talking about these things, but it is actually equivalent, and I will be showing that to you. Probably, definitely not in this episode, but next time. All right, so with the main 2 spaces out of the way, now here we are ready to discuss the third and final space of the 3 that we're going to be talking about. And this one is going to be called a Frolicher space. I really hope that that's how that's pronounced. It might be Frolicher, but I'm pretty sure it's Frolicher. And a Frolicher space is going to be a triple that has a set X, a family of plots, and a family of coplots, such that, and now these 2 conditions hold, P is maximal with respect to smooth composition with C, and I put the ditto marks, but C is maximal with respect to smooth composition with P. So what the heck does that mean? Well, what that means is that P is the largest set of maps, means he has the most possible, so that when I take one map from P and any map from C, when I compose them, I get smooth maps between Euclidean spaces. So that means that P isn't missing any of the maps that smoothly compose with maps in C. And likewise, C isn't missing any of the maps that smoothly compose with maps in P. If there are maps that I can smoothly compose with stuff in my other family of maps, then it definitely has to exist in my family. That's essentially what these things are saying. They contain as many maps as possible so that you can compose them with the other guy and everything still works out fine. We're still talking about smooth Euclidean maps. Okay, and like I said with the Sikorsky space definition, this is also slightly not standard. This isn't the one that Frolicher gave. And that's actually, for the same reason that the last definition wasn't the one that Sikorsky gave. When I defined the family of plots and coplots, I necessarily made them, specifically the family of coplots, it takes maps that may land in any Euclidean space. Just like the family of plots has, any of the domains of any maps in that family of plots could be any one of the Euclidean spaces. That's normal. That's what the Serow definition originally was. But the Sikorsky definition originally only had families of coplots that mapped into R1, only into the real line. And the Frolicher spaces actually had the very similar definition. The family of coplots and plots only mapped into or out of R1. I elected to have them be any Euclidean domain because there are some things that I wanted to do with it. But you could do it the other way too if you wanted to. You could start having, in order to have all the definitions be symmetric, that is, you could have Serow spaces be only have only plots that take in values from the line and land in X, and you can get exactly the same sort of mathematics that I'm going to be doing here, I believe. I'm pretty sure someone has proven, no, it's a component of the proof for Froelicher spaces sort of being equivalent to a type of Serow and Sikorsky space. So it's not for all of them. But regardless, the definitions that I'm using here are slightly non-standard. They are equivalent to the old ones. I will be showing that. And then I will be proceeding onward with showing the original work that was done by each of the three authors on their spaces. And then I'll start to explain some of the more modern stuff that has been done by other authors and that I myself have been working on, because I found some pretty cool things about these guys that I want to talk to you all about. So, now that we've got our three spaces out of the way, we know what it is that we're talking about in differential topology. I'll leave you for this time, and next time we'll talk about how these sets of spaces and the smooth maps on them that we can define actually form categories. So, until then, enjoy yourself, learn you some math, and stay safe. Don't get sick.